Welcome back to Textbook Toonz. To open this vault, we must fill these 9 empty slots using the digits 1 through 9 without repeating a single number. Filling the grid by trial and error is inefficient. There are exactly 362,880 different ways to arrange these 9 digits in a 3x3 space. Instead of guessing, we can use the geometric properties of the grid to solve the puzzle in a few logical steps. This is a magic square. To solve it, every row, every column, and both main diagonals must add up to the same target value. We start with the total value of our digits. Adding 1 through 9 gives us a total sum of 45. This total sum is the starting point for determining the grid's internal limits. The grid contains 3 horizontal rows that, together, hold all 9 digits. This means our total sum of 45 must be distributed equally across these 3 rows. By dividing 45 by 3, we find that each row must sum to exactly 15. This target value of 15 applies to every path in the square: horizontal, vertical, and diagonal. The center slot is the most connected position in the grid. If we place our highest digit, 9, in the center, we would need to pair it with another number. But 9 plus 8 is 17, which already exceeds our target. If we test our lowest digit, 1, and pair it with 2, we reach a sum of 3. To hit 15, the third number in that line would have to be 12, which is not in our 1 to 9 dataset. The center slot is unique because it is part of 4 different lines. By testing each digit, we find that only the number 5 has enough distinct pairs: 5 plus 1 and 9, 2 and 8, 3 and 7, and 4 and 6, to satisfy every intersecting path. Locking in 5 as the center digit provides the fixed point we need to organize the remaining numbers. Now look at the corners. Each corner slot sits at the intersection of 3 lines: a row, a column, and a diagonal. Any number placed here must have 3 separate pairs that sum to 15. We previously saw that the number 1 only has 2 possible pairs: 1, 5, 9, and 1, 6, 8. Because it lacks a third pair, 1 cannot go in a corner. The same applies to 9. Therefore, 1 and 9 must occupy the middle edge slots. With 5 in the center and 1 and 9 on the edges, try to place the remaining digits, 2, 3, 4, 6, 7, and 8, to complete the square. When the edge and center constraints are met, the remaining values fit into place to complete the system. We can apply this to consecutive numbers by using the variable m to represent the center value. The magic sum is always 3m. If 25 is the center, the magic sum for every row and column will be 75. This algebraic relationship allows us to calculate the properties of a magic square regardless of how large the numbers are. Here is your final challenge. Create a 3x3 magic square using the consecutive numbers 2 through 10. Identify the new central number m for this sequence and use it to calculate the new magic sum. Share your center number and magic sum in the comments. Using these geometric rules allows you to solve these textbook problems through logic rather than guesswork. We will see you in episode 4.